All right, folks, so today let's talk about inflection points for a function. So to begin with, let's just recall the definitions of concave up and concave down for a function. So recall that for a function, let's call it f of x. F of x is concave up at a point x equals a if you take the second derivative and plug in that x value, you get a positive result. And concave down at x equals a if take the second derivative, plug in that a value, and you get a negative result. So let's use that to introduce a new term, inflection point. A function f of x has an inflection point if the concavity of the function changes at that point. An inflection point of a function is a point where the concavity changes, either from concave up to concave down, or from down to up. So let's test our understanding of this definition with the following function. Find the values of x at which this function has an inflection point, and we're given this polynomial. Now, if concave up means that the second derivative is positive, and concave down means that the second derivative is negative, then the function is likely to change concavity at a point where the second derivative is exactly 0, because 0 is right in between positive and negative. So let us take this function, let's find its second derivative, and let's investigate the points where that second derivative is 0. So finding an inflection point is almost like finding a critical point, except critical points deal with the first derivative and inflection points deal with the second derivative. Applying the power rule here, we have power rule on x to the 5th. 5 comes down. 4 comes down. 3 comes down. And 5 vanishes. And then passing to the second derivative, we have x cubed. We have 2x squared. We have x. So this can be factored first by pulling out x, and then by factoring further. So let's check and see where this function equals 0 to get an idea of where this function's concavity might change. And we have 2 points at which the concavity is 0, namely x equals 1 and x equals 0. But are both x equals 0 and x equals 1 guaranteed to be the location of inflection points? It's not guaranteed because it's possible that f double prime will be the same side on either side of these inflection points or candidates for inflection points. So what I recommend is to go in and do the same sort of sign chart process that you did when you were using the first derivative test. Choose some potential test values of x in between these values, which made the second derivative 0. Plug them into the second derivative and check and see what will be happening to the sign of the second derivative. So if I plug in -1, for example, to the second derivative, the result of this will be a negative number. If I plug in 1/2, the result of this is a positive number. If I plug in 2 minus 1 squared to the second derivative, the result of this will be a positive number. So as the function passes across x equals 0, the function changes from concave down to concave up. the concavity changes. So x equals 0 is an inflection point. But x equals 1 is not an inflection point because the concavity of the function is concave up both on the left and the right-hand side of x equals 1. So x equals 0 is the only inflection point of this function. So to summarize the general process, we are asked to find inflection points. Start by finding the second derivative and setting the second derivative equal to 0. And align those values on a chart like this one. Then choose test values of x in the neighborhood of your numbers, your zeros for the second derivative, and check and see if the function's second derivative is actually changing sign as you pass across those zeros.